Alright guys, welcome back to Algebra 2. We're talking today about some permutations and combinations. But before we get into that, I want to answer the question that I know a lot of you guys have. You guys watched the video from yesterday and hopefully you tried out those factorials. And a bunch of you guys are thinking, wait a minute, 0 factorial. Based on our definition, 0 factorial should be 0. It doesn't have any numbers smaller than it, all the way down to 1. Like technically 1 is a bigger number than 0. So 0 factorial should be 0, or it shouldn't exist. But if you put it in your calculator, what did it tell you it was equal to? It said 1. What the heck is up with that? This is where math gets a little weird. And math starts to, we start to think about it not necessarily in what makes mathematical sense, but in the reason why we're doing this. So mathematically, 0 factorial should be 0, plain and simple. However, the reason factorials exist is for us to figure out how many different groups or combinations of something you can make from this number on down. I know that seems weird, but it's just kind of the reason we do it, and you'll see that more once we get into permutations today. So the idea is that if you don't have any members in a group, that if you have 0 people, and you want to know, well, how many different ways can you select a group of those 0 people? Well, there's only one way to choose that group, and that group is picking no one, right? It's kind of weird. This is one of those mathematical anomalies. It doesn't make sense, but for the purposes of what we're trying to do with it, we just have to accept it for what it is. And 0 factorial is in fact 1. Whether or not you understand the idea behind it, as long as you just kind of accept that as fact, you're fine. So what we're going to talk about today, though, is permutations. Permutations is the idea that we have a whole bunch of people, and we need to select a group of them. Now, permutations is one way of selecting a group. The other way is called combinations. And what I really want to talk about is the difference between these. Because we're going to talk about them both. Both of them come up. Now the difference is, let's say all of us in this class are going to participate in a race, right? Now, if you're going to participate in a race, you're going to go and run the mile, and we're going to see who can finish it the fastest, that kind of thing. And we want to award the top 3, like the Olympics, gold, silver, and bronze. Now, if all of us get out there on the track, run the mile, and then we have the first 3 to finish, does it matter the order of which those 3 people finish in? Let's say, I don't know, who's in Algebra 2? I've forgotten by this point. Let's say we have Zoe, Lainey, and Emily all finishing first 3, right? Does it matter for the purposes of a race if it was Emily, then Zoe, then Lainey? Or if it was Lainey, then Zoe, then Emily? Well, absolutely it does. We said that we wanted it to be like the Olympics, gold, silver, and bronze. It matters that whenever we say, those first 3, that group of 3, it matters the order that they are in. That's a permutation. If we're talking about a probability or statistics problem that says we need this group of people, a permutation says it is critical the order of which they are chosen or selected or finish, and if it's a race or whatever. A permutation says it matters the order that they finish in. That first, second, and third are unique places, and it's important that we observe that they are unique. Usually, we're going to get questions something like, 20 people start a race. How many different ways can they finish first, second, and third, right? How many different ways is it possible for that to happen? And since we care about first, second, and third, since first is different from second and is different from third, then we are finding the permutations, all of the different ways that 3 people can finish the race where order matters. That's really the key word here. Order matters. Now, you probably assumed that if order matters in a permutation, that it doesn't in a combination, and that's exactly right. Order doesn't matter. So let's think of an example where the order doesn't matter. Obviously with a race or something, it does. First 3 to finish. Or maybe if we were taking a test, we want the top 3 high scorers. You probably care if you're number 1 or if you're number 3, right? You want to be the best. But let's say instead, I ask a couple of people to help move some boxes, right? Like, I need to get some stuff out of this room and move it to the other room. So I ask Harley and Toby and Christian to help me out. Does it matter that I asked Harley and Toby and Christian? Is that different than asking Toby and Christian and then Harley? Not really. I mean, those 3 people are still going to be the ones helping me pick up the boxes and move them wherever they're going. There's no real difference in the order of which they are selected. Now, if it was a race, there is. But they're just a group of people that are going to go help move something, right? So that situation, saying, I have 20 people in a room, how many different ways can I choose 3 people to help move something? Well, order doesn't matter there. They're just a group of 3. So that would be a combination. We're going to talk tomorrow. No questions or work today. We're going to talk tomorrow, I guess Monday, about how to solve problems that deal with permutations and combinations. We're going to keep working through this packet. If you have any questions about this right now, email me. Otherwise, I'll see you guys on Monday.